We just finished discussing mass, and it was kind of a short discussion, but we will see mass in today's calculations, and we are trying to discuss center of mass. So let me take you to something that you might have done with childhood to think about the concept, and this will really motivate some formulas that we will see. And that is this. So this is sort of a picture, it's supposed to be, of a seesaw. And you might remember okay, so how does the seesaw work? If you remember from your childhood, this was one of my personal favorite things to play on at the playground. One kid sits here, one kid sits here, and they can go back and forth, right? But the question is, can you, and you might have tried this many times, can you balance it? Can you have one kid on each side and then both be in the air at the same time? And you don't necessarily need the kids to weigh the same, or another way to say that is have the same mass. You don't need that. In fact, what you might remember is if you put the bigger kid closer to the center, then you can balance on a seesaw with a smaller kid further out and the bigger kid closer to the center. Okay, so what am I really saying here? Well, if we have this, we think about this mass as being a block and this mass as being a block, and for the purposes of my thought process, I'm not really considering mass along the seesaw. To balance, we need that this mass, m1 times d1, that distance is m2 times this distance. And what this would say is just what I mentioned, that if you have a heavier kid and you make the distance shorter to this center place, then it might balance, it might be equal if you have a lighter kid and he's further away. Okay, so this notion of where to put this fulcrum here, if you think about the two kids now being fixed and I just move this around trying to get the balance, is called the center of mass. So the center of mass. And this is denoted x bar. And this is the location to place the fulcrum for balance. Now, I'm going to come back to this exact example in a minute. It's really great for motivation and for seeing some of the formulas. But what would this mean? For example, we want to look at thin wires. And this we can actually think about center of mass. This will be the first thing that we come to. If you have a thin wire, maybe I'll put this in stars, for a thin wire, and this is a wire where it's not just going to be constant density, it's going to be a variable density, just like we had in the last section where we calculate the mass. So you have a variable density. In that case, center of mass is not going to be necessarily in the direct center, but for a thin wire, the center of mass, x bar, this is where you would place your finger to balance it. It's the same idea, to balance the wire. So there is some location on the wire such that if you put your finger there, you will have it perfectly balanced. And like I said, it's not directly in the center when you have variable density. Okay, but let's return back to this seesaw type example, but I will simplify the problem for a moment. So let's suppose we have an axis, okay? And then we have just think about a mass living on top of a point, and this is m1. This is this mass. And this location, then I have this mass, m2, and this location here is x1, and this location is x2. Okay, so we're thinking about all of this mass concentrated on just a point. The mass is M1, and we're located at x value x1, and similarly for this one. And then somewhere here, maybe it's here, is the center of mass, x bar, okay? So what would this mean if we think about this equation? We would need, well, we need, okay, we need M1, this mass, times this distance, which is x bar minus x1, to be equal to, and now we take here, this M2 times that distance would be M2 times x2 minus x bar. Now I'm going to try to use this to solve for center of mass, right? And I have just 2 points, and I think about all the masses being in the point, and they're along a line. This is the situation I'm considering. Okay, so I have M1 x bar minus M1 x1 equals M2 x2 minus M2 x bar. And now I'm trying to solve for x bar, so I move everything with the x bar on one side. Everything else goes to the other. And so I have, on this side, I could have M1 plus M2 x bar. And this equals, move it over here. We have M1 x1 plus M2 x2. And the final step, I just divide. So I have x bar is equal to M1 x1 plus M2 x2 divided by M1 plus M2. This is the center of mass. Now, I'm about to, maybe even before I erase, I will write this generally. If we had, say, m masses at points along a straight line, it's almost exactly this formula. But before I make that observation or make the statement, I want to look at the denominator. What you notice here, this denominator here, is it's the total mass. The denominator is the total mass because I'm only considering the masses of these 2 points. Okay, 2 points. M1, M2, the total mass, you just add it up, okay? And so we have this M1 x1 plus M2 x2 divided by the total mass gives us the center of mass. Okay, well, what if we had, let me make a little box, and this is a comment, and then we will get to the thin wire situation. Okay, comment. If we have n masses, make my box a little bit bigger, n masses along a line, so the mass mi is located at, let's say, xi, and these are just masses along a line, then it's almost the exact same formula holds. It just generalizes. Instead of adding 2 like this, the center of mass, x bar, is, well, you add up mi xi and then divided by, add it up, just mi, okay? It's the exact same formula. You divide by the total mass here, and then you take and you add up mi times xi, I equals 1 to n. We have a thin wire. Okay, wonderful. Thin wire. with density delta of x, okay? If you had a thin wire with constant density, well, it would be directly in the center, okay? Would be the center of mass, and that wouldn't require calculus. With variable density, like I said, this does require calculus, so we have this line between x equals A and x equals B. Okay, so here's my picture. Well, I don't even need a y-axis. I'm a thin wire. Here is A, here is B, and maybe again, like when we are doing mass, I will shade my wire in blue. Okay, well, can you imagine what I'm going to do? Subdivide into intervals. So we subdivide such that, just like in the last video, the density, so we subdivide A to B into n subintervals. Subintervals of length delta x, which is b minus a over n. And we can pick n so large such that the density is approximately constant, right, on each subinterval. Okay, now, maybe I will even do this. We have A is x0 less than x1 less than xn, which is, oh goodness, I am almost out of space. I will fit the B in there. So this is our partition, and I have drawn it here. Okay, well, how are we going to do this to calculate center of mass? We can't imagine. Okay. We can approximate the center of mass x bar by considering the wire as in points with mass. Well, now we have a mass calculation. Okay, the mass is, I'll say the mass on the point this. So I'm considering this is approximately a point, this little subinterval, which is a little bitty chunk of wire of length delta x, but the mass is this is approximately, well, this was the last video. What is mass? It's density delta, let's say of xi, times volume, which in this case is delta of x. Okay, so this is the approximate mass. And then, now, what do? Well, the center of mass, x bar, is approximately, well, in the numerator, we have a sum. Maybe I should make this a little bit bigger. I equals 1 to n of, it's the mass times xi, right? You add up, you have a bunch endpoints, we just saw this. You take each mass times each x coordinate, and this gives you, so we would have a mass. This is the, quote, mi, the mass, and then times the location. This is in the numerator, and then in the denominator, we need total mass. So we add up the masses. I equals 1 to n. We add up the masses here? Well, okay, to get to the numerator, we could find the exact numerator for the center of mass by taking a limit as n goes to infinity. Same thing for the denominator, right? It's really remind sum, if you want to think about it that way, but I'm thinking about them both at the same time. So we get from this that x bar equals, okay, I can translate this and this to integrals. The Riemann sum and thinking about this as in sort of point masses helps me set up the correct integral, excuse me. Here we go. It's an integral from a to b of x, right? This is when we sort of convert to an integral, this becomes a dx. So I'll put that out here. So I would have an x delta of x dx divided by an integral a to b of just delta of x dx. And sometimes, so this is, maybe I should even put this a little bit differently, goes here, like this. Let me talk a little bit more about this, then comes example. Okay, so here, the denominator, this is the total mass. This is what we discussed in the mass section. This is the total mass, capital M, total mass. And the numerator, this is what's called the x component of the moment. And what you see in your text is sometimes it'll just be written m x bar. Well, because of x bar is this over m, if you multiply through by x bar, then you get what's in the numerator. Okay, so that's just sort of a comment as to what you will see. Okay, now let's do an example, and then we will get to the two-dimensional case as well, where we have a metal plate. In the metal plate, though, we have not only an x bar, which is an x location, but we will have a y bar. So the actual center of mass is a tuple. It's an x bar, comma y bar. But before we get to that, let's do an example of the thin wire where we will calculate all of these quantities. So we'll need to calculate mass, that's in the denominator, and then calculate this x bar, which is the numerator. Then we take the quotient to get the center of mass. Okay, so let's see what example I want to do. Okay, example. A wire has density delta of x equals 4x squared plus 2 from x equals minus 1 to x equals 3. Find the total mass, and then we will find the center of mass. Okay. Well, the total mass, this is what we talked about last time. Although I didn't do a one-dimensional example, I talked about it. My examples are two-dimensional because they're more involved. But the total mass here, we will do this now, we just integrate minus 1 to 3 of the density function dx. Okay? Not too bad of a setup, right? Well, here we go. We have 4/3 x cubed plus 2x We evaluate between -1 and 3. When we evaluate at the upper limit of integration, we get, let's see, 3 cubed, well, we have 9 times 4, we have 36, plus 6, subtract. Now we evaluate at the lower limit, we get a -4/3, and then -2. So altogether, we get, maybe I should move my equals way over here. We get, let's see, 38 plus 6 gives me 44 minus 4/3, plus 4/3, excuse me, becomes, let's see, 45 and 1/3. Or if we multiply 45 times 3, we get 90, and another 45 gives us what? 135 plus 1, 136/3. This is the total mass, capital M. Maybe I will put a box around this because this is the first part of the problem, and we need this in order to get to center of mass. Now we can think about this mx bar if you want. This is the x component of the moment, or you can just think of it as the numerator in the center of mass. Well, this was an integral, -1 to 3. You take x times the density. This would be x times 4x squared plus 2 dx. Okay? Well, I'm going to distribute, so I have an integral, -1 to 3. I have 4x cubed plus 2x dx, which is, now I integrate, I get x to the 4th plus x squared, okay, evaluated between -1 and 3. So 3 to the 4th is the same thing as 9 times 9. We get 81 plus 9 minus, and then these are both 1. 1 plus 1. So I get 81 plus 7 in a way. Okay, we have 88. 88. Okay. This is the numerator, or the x component of the moment. The x bar, the center of mass, 88 over 136/3. Okay, now we invert, multiply. 88 times 3. That's something that I don't do so well in my head. Let's see what I got. We have 264. 264 over 136. Now you can simplify this if you wanted to. This is 33/17. That's in simplified form. Personally, well, okay, fine. This would be our center of mass. And if you just think about it, first of all, you know, sometimes, a lot of times in fact, with applications, we have little sanity checks. If the wire lies between -1 and 3, okay, so we have a wire and it lies between -1 and 3, well, the center of mass better be between -1 and 3. This is approximately 1.94. So in terms of our sanity check of it lying between -1 and 3, it definitely does. So suppose now we have a wire with constant density. And the density is just delta, okay? And we want to and this lying between x equals a and x equals b. Now, what I told you, right? I said that wouldn't require calculus. We know the center of mass would be right in the middle. So let's show that x bar, well, the middle is the average of the two. It would be a plus b over 2. Okay, but we're going to show it using these calculations of the integral. It's a nice exercise. Okay, wonderful. Well, first of all, let's get the total mass. This is an integral from a to b of just delta dx, which this is a constant. And so this is just going to be delta b minus a. And then this x component of the moment, or you can think numerator, it's going to be an integral a to b of x delta dx. So x times the density, and well, this is a constant, so we just have x squared over 2. So this is, maybe I will write the step here, evaluated between a and b. This is delta. This is b squared minus a squared over 2. Okay, great. Now, what's the center of mass? So x bar equals, we take this x component of the moment divided by total mass. So we have delta. We have b squared minus a squared over 2, and then divided by delta b minus a. Now we can simplify. This is in the denominator with the 2. So we have a delta over b squared minus a squared. Okay. Then we have a 2 delta and a b minus a. Maybe you see it. The deltas cancel. And be careful. This is the only time they cancel. If you have some function of x, the deltas won't cancel off. You have to integrate this, integrate this. You can't factor out a function of x from an integral, for example, unless it's constant like it is here. And what I can also do is, you see my numerator, it is a difference of squares. So first of all, I'll cancel the delta, and then I factor the numerator in the same step. I have 2b minus a, and then now we have, because b minus a over b minus a cancels, we get b plus a over 2, which is exactly, well, okay, I have it a plus b over 2, it's the same point. So you see here, what I was mentioning is this, if you have this wire with a constant density, the center of mass is exactly right in the middle. Now, let's see. Let's do one more example with a wire. Okay, first of all, the total mass, capital M. This is an integral, 1 to 3. It's the not x. That would be the x component of the moment. It's just e to the x dx. This was the last section. Now this is one of our favorite functions to integrate because we just get e to the x when we integrate. So I have e to the x like this, and we get e cubed minus e. This is the total mass m. Oh, maybe I'll even put to the 1. Fine, okay. Here's the total mass. Now, this part, mx bar, which is the x component of the moment, or another way to say it is the numerator. When you do center of mass, we integrate 1 to 3 of x e to the x dx. Okay? By parts, liate. I hope you see that, right? This is one of our first examples we ever did by parts was x e to the x. We have algebraic, so that means maybe I'll do my work in black for u dv like this. So we have u is x, dv is everything else. Then we differentiate. Then we integrate. And then we have uv minus the integral of v du. Now, in the last video, mass, when we did the mass of a metal plate, I took the time, found the antiderivative, then went into the definite part when I had it by parts. Maybe this one I'll just jump into the definite part. Either way is really okay. So this would be, we have uv x e to the x, evaluated between 1 and 3, and then minus the interval 1 to 3 of v du, like this. Now I can continue. This would be 3 e to the 3 minus e to the 1, and then minus e to the x, evaluated this part between 1 and 3. Maybe I'll put a parenthesis here. Just this is being evaluated. These first two terms came from here. And I'm almost done with this. We have 3 e to the 3 minus e to the 1, and then a minus e to the 3, and then plus e to the 1. Minus, a minus is a plus. This simplifies to 2e to the 3. 2e to the 3. Well, this is this x component of the moment in x bar. Now, all I need to do is take this, divided by this, I have center of mass. So if we do this, x bar is, I take this part, divided by this part, and this is my center of mass, okay? Now let's see, did I see what that was approximately? Oh, yes I did. Like I was saying with our sanity check, it's good, it's fine, leave your answer exact, no problem. But let's say this number was 5, we would have made a mistake. Okay, or the number was -10, made a mistake because the wire only lives between 1 and 3. So the place where you put your finger to make it balance only makes sense is between 1 and 3. This is approximately what? 2.313, okay? Which, as a sanity check, is good. It's a number between 1 and 3, and you certainly see that e to the x is increasing. You're going to have a lot more of the mass as you go higher on the interval, and so having a larger number, or a number bigger than 2, certainly makes sense, right, for this center of mass. Okay, so next we're working with a metal plate. Okay, so we now have a metal plate. And I will draw the picture, or a similar picture I should say, as when we were doing mass. So the plate lives between x equals a and x equals b, and we have some function here, y equals f of x, and another function, maybe I'll do this one in green, that's below. This one's y equals g of x. And then our plate is here, between x equals a and x equals b. Okay, so the plate lives here. Okay. Well, I want to color it in, but I want to do some other things. Okay, well, in this case, the center of mass to be some location. And well, I should also say we have some density function that only depends on x. Okay. So the center of mass is going to be some x bar comma y bar, where if you think about taking this plate, well, you would have this one location, wherever it is, and if you put your finger there, it would balance, okay? But I'm not really going to think about this, calculating this vector style. That's a different approach. I really want to think about finding x bar and y bar separately. So first, well, maybe for both of these, we would do the exact same thing as we have done in many applications now, and in particular also for the center of mass of a wire, we subdivide this into n subintervals of length delta x, capital delta x, which is b minus a over n. And n is so large, and we assume n is so large, maybe I will put the partition first. And then the density is approximately a constant on each subinterval. Okay, so we can take n so large such that this is the case. Now, well, the x component of the center of mass is exactly like the last example. Let me draw a very small n. This is not very many points in my partition, but it's just an idea. Really, we would have n quite large to make this close. Now, for the x component of the center of mass, not much has changed. We think about this whole slice as being just a point, which you can take if delta x is very small and is very large. You can take the point to be the left, the right, or the midpoint. You think about all of the mass of this rectangle to be all concentrated at the point. So the center of mass, or maybe I should do this, the x component of the moment would be approximately, well, what would it be on one chunk? And then I will add up I equals 1 to n. Well, I need the x coordinate, which is, let's say, xi, times, then I need the mass, right? Well, the mass is density times volume. Okay, this is what we did in the last section. The volume here is an area, because we're working in 2 dimensions, so it's a height times delta x. So this would be f of xi minus g of xi delta x. And again, we know what the mass is. Maybe I will just do my calculations for mx bar. This is now, we can convert this to an interval. It would be x, delta of x, f of x minus g of x, dx. So this is the x component of the moment. It's the exact same thing that we saw, almost the same, with the one-dimensional case, except now we have to factor in that the mass is not just the density times delta x. We have this 2-dimensional volume happening. And here, x bar, the center of mass is this, x, delta of x, and then f of x minus g of x dx over, well, the total mass, just like we saw in when we had a wire. And the total mass, I didn't do it in the Riemann sum notion this time, because just because we know the total mass. Like this, and then it's just density here. F of x minus g of x dx. Although I typically won't just jump into this fraction, as you've seen in the examples of a wire, I calculate the total mass. So down here, this is the total mass, often called M. So what I do and what I will do is I calculate the x component of the moment, then I calculate the total mass, or you can calculate one before the other, and then I divide, okay? And make sure you don't just cancel off the delta x's, this delta of x, the density, because it doesn't work like that. They're a function of x, as I was saying. You can't just factor them out of the two integrals and cancel. Now, this is not that much different than thinking about the thin wire, but now let's talk about this. The y component of the center of mass, and then we will do some examples. Okay, let me erase. In fact, some of this I can keep here, 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 here. I'm keeping my subdivision, okay, but the y component of the center of mass, y bar, or the y component of the moment, which is what's in the numerator, will look different. Okay, but it's not too terribly bad. Let's go back and think about this same subdivision, etc. But I want to think about y values. So now I still have these 1, 2, 3, 4 rectangles. And I still want to think about the rectangles as being all concentrated at a point, that all of their mass concentrated at a point. But it's not a point because you think about, if we go back to when we have just points, you add up the locations times the mass divided by total mass. Well, here, this is y component, so my locations must be along the y-axis. So maybe let me write something. We will think about the rectangles in this Riemann sum because I'm interested in y bar. Now, these we will think about them or as points along the y-axis with all the mass at that point. And then once we do this, we can just, in the Riemann sum, add up location is going to be a y value times mass added up 1 to n divided by total mass. And we have a formula for the y component, y bar. Well, how are we going to do this? You see, if you think about delta of x, which is here, getting very, 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 very small, okay? It's different, as I mentioned, than the x, because in the x's, if we want these to be points along the x-axis, it didn't really matter with delta x small whether we use the location to be xi minus 1 or xi or the average, the midpoint xi plus xi minus 1 over 2. Because delta x is so small, well, it doesn't really matter. All of those are very close together and they all work. But if you take delta x so small, what happens with the y values is the y values don't get any closer together. What really happens as delta x goes to 0 or as n goes to infinity is that these rectangles become a wire, right? They become a thin wire with constant density. Okay, so how are you going to represent that as a point here on the y-axis? Maybe I should even draw the y-axis extended. Well, okay, if we have a thin wire, or you imagine delta of x is very, very small, the location, the only location I would say that would make sense for how to represent this whole wire as a point where all the mass is concentrated is the center of mass of that wire. Okay, so now we have a wire. And delta of x is constant. What's the center of mass? Well, halfway in between, right? So the y part here, the y part, I'll put the location of the point that we would make for this rectangle on the y-axis would be, so like I said, this is now thought of as a wire because delta of x is so small, and a wire with constant density has center of mass halfway in between. So for instance, on this subinterval, this one is labeled delta of x. Halfway in between is maybe here, and so the point would be here. And we would put the whole mass of whatever this is, right? So the location is f of xi plus g of xi over 2. So this is my location here, where I'm going to concentrate all the mass of this rectangle. Okay, this is the most important step to seeing the formula. So now, if I do this, my bar, which is the y component of the moment, or you think about it as the numerator in the calculation for center of mass of the y bar. This would be approximately a sum I equals 1 to n. Well, I take the location f of xi plus g of xi over 2, okay? And then I'll have different locations for each rectangle. And then I multiply by location times mass, right? It's the exact same thing we did in the x-coordinate. We just have to think a little bit more about location. Well, the mass, not much has changed. We have density, we have volume, and again, my volume is a two-dimensional volume. It is area, so this would be f of xi minus g of xi times this capital delta of x, height times width is an area. Well, in this case, it's volume because we are two dimensions. Then we multiply by density. So this is the location. All of this is mass. And so we see it's the exact same idea as when we looked at the x component, or even the wire, where we think about just having points add up location times mass. This gives us the numerator. And then the denominator is the same as with the x component. It's the total mass of the plate, which is going to be an integral. So maybe I will erase this part. I'll keep my picture, and then I will be able to write my two formulas. We can then do an example. Okay, so we see the following. We see, my bar equals, well, this is it written in as an approximation of a rearranged sum. There will be an integral. So what will be an integral? A to b. Well, we take f of x plus g of x over 2, and then we have delta of x, f of x minus g of x, and then dx. Now, I will say you can, this is the way to sort of remember it. If you forget, you can construct this again, although that might take some time. You can write this more simply. maybe let's do it now. How else could we see this? And this would be if you like looked up the formula, what would you see? Well, you see we have this plus this and this minus this. It's really a difference of squares. So we can write this as follows. We have a 1/2. We have f of x squared minus g of x, parentheses squared, delta of x dx, okay? Because when you have this plus this minus this is a difference of squares. But I didn't want to just hand you this formula because you don't really have any intuition of where it comes from. It comes from the exact same idea as we have discussed that the x component comes from, which is thinking about these point masses along a line. We just have to think a little bit more. Okay, so this is m y bar, and then the center of mass would be this of 1/2, we take this difference, squared minus g of x squared delta of x dx, and then we divide by, let me erase, this part, maybe just this location, so that I can fit my whole y bar. We divide by the total mass, which is an integral a to b. We just integrate density times f of x minus g of x dx, okay? And as I mentioned, when we were talking about the x component, this is total mass, capital M. Okay, now let's do some examples calculating center of mass for a plate, so it's something two-dimensional. And the first is this one. Let me graph. So we have a metal plate. Here's some axes. And it lies between x equals 1 and x equals 2. And let's see, we are told the density function is x squared. It's bound between the x-axis, that would be here, and then 2 over x squared. So at x equals 1, 2 over x squared is 2. And at x equals 2, 2 over x squared is 1/2. So we are maybe here, and then the curve is something like this. It doesn't have to be perfect in this case, just to get an idea with the picture. And then my region, this is y is 2 over x squared. And then the region is here. Maybe I will put this, and then this is the bottom part of the region. And we imagine this being a metal plate with density x squared. Okay, wonderful. Well, this is two-dimensional, so the center of mass will be a tuple. It'll have an x component, a y component, and both of them we know in the denominator it has the same thing, which is the mass. So maybe the first thing I'll do is calculate the mass of this plate. This was what we did in the last section. So the total mass, capital M, it's an integral from 1 to 2. We take upper minus lower. Well, the lower here, maybe I'll put this as a note. My upper function, okay, fine, is 2 over x squared. But my lower function that bounds this plate is 0, okay? So my mass, we take delta of x, and then we take upper minus lower. I'll actually write minus 0 just so we can match it to everything we've done, and then dx. And if you think about it from a Riemann sum perspective, this is the density. This part would have had a delta of x, and it would be volume, which is area in 2 dimensions, because this would be the height, this would be the length, like this. This is where this came from. But now, this is not very difficult to integrate. The x squareds cancel. We're integrating 2. And our derivative is 2x. When we evaluate here, we get 2 times 2 minus 2 times 1. We get 2. Okay, so this is the total mass of my plate. Maybe I'll write that in blue, what this is. This is the total mass of my plate. Then I need to calculate the 2 numerators in my coordinates. One was called the x component of the moment, the other the y component of the moment. So here we go with this. For this mx bar, which was the x component of the moment, we integrate, well, we had x times the density, maybe I'll write it here, and then we had, because this is our first example, I'll actually write it upper minus lower, like this. And in this situation, it's not too hard. Maybe I can even write it over here. We have the integral 1 to 2. So we have x. The density is 2 over, the density, excuse me. I was looking at the wrong thing. The density, that's why it's good to start this way, that I have my integral set up right. The density is x squared. Okay, and then my lower is 0, so I just multiply by the upper. Okay, maybe I'll write it here. Minus 0, dx. I should have made that 0 smaller. dx is very little. I ran out of space. Okay, which is, well, the x words cancel. This is an integral 1 to 2 of 2x dx. Okay, and this is just x squared between 1 and 2, which is 4 minus 1. We have 3. One more thing to calculate, and then we can get our center of mass, the x bar, the y bar. But the last thing we need here is y bar. This is the y component of the moment. And what we did here is, instead of having this x in the Riemann sum, remember it was the average of the two. So we had f, well, there's a 1/2. Maybe I'll put that in front. And then we have f of x plus g of x. And then we have delta of x. And then we have f of x minus g of x. And you could, as I simplified, if you want to remember the formula as a difference of squareds, there's no problem with this. You could also remember it like this because it matches a little bit more closely to the formula for the x component of the moment. Now in our situation, we have the integral 1 to 2. Well, you see, maybe this time I'll leave off the zeros. Down here, g of x is 0. So we just have 1/2. F of x is 2 over x squared. Okay, and then delta of x is x squared. And then we have another f of x because we're subtracting 0. And this one, we were adding 0, but we have another f of x. Okay, now, well, we don't just cancel everything because not everything cancels. You would cancel this 2 with this 2, this x squared with this x squared. You're left with a 2 over x squared as the integrand. So this is the integral 1 to 2 of 2 over x squared dx, which is, well, this is a minus 2 power. We'd add a power, divide by the higher power, but we have minus 2 over x from 1 to 2, which will be -1, oh goodness, plus 2, right? Evaluate at 2, -1. Evaluate at 1, and subtract plus 2, so this is 1. Okay. So the y component of the moment, we have 1. Now, maybe I thought I was going to race to finish the problem. Maybe I can just use this box and make every single use of every single possible space on this little board. So then, if we want x bar, we take, well, it's this divided by the total mass. So we take the x component of the moment divided by the total mass. This would be 3 over 2. And then, if we want y bar, we take the y component of the moment divided by the total mass, 1 over 2. Or, if you write it as an ordered pair, as a point, for example, in the plane, we would get 3/2, comma, 1/2 for our center of mass as a point in the plane. Now let's maybe just shade this in. 3/2 is halfway in between here, and 1/2 is here. Our center of mass is right here. Well, it's thickened. Hopefully you can see that color. Okay, this is our center of mass for this region with this density function. Okay, first of all, there's a new word here. And what is this? What is centroid? Well, centroid is center of mass, but this is center of mass with constant density. Might as well use that delta is just 1, okay? And you could put a delta in every integral you calculate, but it's just another symbol to keep track of. In the end, when it's constant, the deltas will cancel out of the fraction. So I'm just going to use delta's 1. Now, let's get to the problem. We have a region bound by 2 curves. We need to set them equal and figure out what our region is. So we set the 2 curves equal. X minus x squared is negative x. We have 0 is x squared minus 2x. This is not challenging to factor. From this we see that x is 0 and 2, and the points on the graph would be 0, 0, and 2, comma, negative 2. And so let's just graph it, maybe up here even. One's a line, one's a quadratic. Because of the negative on the x squared, it faces down. Both of these we can graph without too much difficulty, although you do have your graphing calculators. So we will go out 1, 2, 1, 2, and it intersects here, and it intersects at the origin. Okay, so this is 1, 2, minus 1, minus 2, okay? And then one of them is a straight line. This is the line, y is minus x, here. Now, the other one's a quadratic. You notice at 1, we are also at 0. So this here. And if you wanted to figure out where the local max, I will say, is, you could just take this and differentiate it. You'd get 1 minus 2x, set it equal to 0. X would be 1/2. So the highest point here will be at 1/2 something, whatever that is at 1/2. You could find out exactly. I'm just trying to graph the general shape. And then it's a quadratic pointing down or facing down like this. So this top function in blue is y is x minus x squared. And then centroid, this means, as I mentioned, constant density. I will just use density as 1. Why not? It simplifies things. Okay, So first of all, let's calculate the total mass, m. This is the total mass. This is an integral. Well, my x's range here, 0 to 2. 0 to 2. And then, well, we would have density, which is just 1, then times upper minus lower. So we would have x minus x squared minus x dx, which is an integral 0 to 2 of 2x minus x squared dx. Okay, so then we integrate. We have x squared minus x cubed over 3. And we evaluate between 0 and 2. Well, evaluating this at 0 gives 0. So we can just evaluate at 2. We get 4 equals 4 minus 8 over 3. 4 is 12 over 3. We are left with 4/3. This is our total mass. Total mass. This will be in the denominator of both the x bar and the y bar. Okay, now, very good. What do we need next? We need the x component of the moment, which we integrate. Now, it would be x times delta x times upper minus lower, right? But we already know upper minus lower is this, simplified, and delta is 1, okay? So this x component of the moment is just x, or the integral of x times this thing, which is upper minus lower. So we have 2x minus x squared dx. And this is an integral, 0 to 2. We have 2x squared minus x cubed dx, okay? When we integrate 2x cubed, we have 2/3 x cubed minus x to the 4th over 4. That was integrating x cubed, right? These integrals are not hard. The hard part of this is the setup, and then at least in this problem, just like in the last one, the integrals are just polynomial power rule. And we evaluate 0 to 2. Okay, well, 2 cubed, 8, 2, we have 16 over 3. And then 2 to the 4th is times 4, 16 over 4. This is going to be a minus 4, which is 12 over 3. Well, we get another 4 over 3 for mx bar, okay? Good. One more thing to calculate, and then we can start dividing. We need the y component of the moment, which is an integral, 0 to 2. Okay, let's think about this, right? Delta of x is 1, constant. In this case, we use 1. Instead of the x, well, we still have this part, but instead of the x, we add, right? And we have a 1/2. So instead of the x, it's like an average. So we have a 1/2. We add the two functions, which would be x minus x squared, and then we add. Okay? So this is the 1/2 f plus g times 1 for the density, and then times, well, we still have upper minus lower, which is simplified here. So this is upper minus lower, it all came from this. The upper minus the lower here is 2x minus x squared. And now something simplified because we have an x minus x. This is an integral, 0 to 2. We have a 1/2. The first term is just minus x squared. And then we have a 2x minus x squared. Okay, one more thing I can do here. maybe I will go to the next line, is as follows. It's an integral from 0 to 2, 1/2. We have minus 2x cubed. We have plus x to the 4th dx. Okay, now my very last step is to integrate, evaluate, then I will be able to figure out x bar, y bar just by dividing what I already have on the board. Okay, so this is, we have 1/2. Then we have minus x to the 4th over 2 plus x to the 5th over 5, evaluated between 0 and 2. Maybe I will come down here and I will leave this tiny piece of room here. I use every space I can. I will leave that for the calculation of x bar and y bar. Okay, here we go. Well, again, when we evaluate this at 0, we get 0. When we evaluate at 2, we have 1/2 times 2 to the 4th is 16, so this would be minus 8, and then plus 2 to the 5th is 32, we get 32 over 5. This is the same as negative 40 over 5 plus 30, so this is going to be a negative 8 over 5. This becomes negative 8 over 10, which is negative 4 over 5. Okay, now, it's negative. Is something wrong with that? Did I make a mistake? I mean, you should ask that, right? Well, no. In fact, I would expect negative. You see, this is the y range. Well, I never found this y value because I didn't evaluate, but it happens at 1/2. We have 1/2 minus 1/2 squared. 1/2 squared is 4th. So this is at 1/4. Maybe I should have done it just to think about it. This here, this local max happens at y equals 1 over 4. Just evaluating this at 1/2, right? 1/2 minus 1/4. Very good. So what you see is that the y's on this region range between minus 2 and 1/4. So getting a number, well, we don't yet have y bar, but we can see it's going to be negative. Getting a negative number is not a problem because our y's range over negative values. Okay, now let's finish down here. Maybe I will switch to blue for my final part of this problem. To find the x-coordinate of the center of mass, well, both of these we divide by the total mass, and we take 4/3 over 4/3, which is just 1. Okay, we took this x-coordinate at the moment and divided by the total mass. It gives us 1. Okay, the y component of the center of mass, we take the y component of the moment, negative 4 over 5, divided by the total mass, 4 over 3, which is negative 4 over 5 times. We invert, we multiply, becomes 3 over 4, which is negative 3 over 5. Okay, or the ordered pair I will put below is 1 comma negative 3 over 5, like this, okay? This is the centroid of this region, which just means the center of mass when you have constant density. And if I think about it on my graph, I go out by 1, okay, and then it's negative 3 over 5, which is a little lower than 1/2. So it's somewhere right here, maybe, like this. Okay, I fattened it just so you could see, but this is approximately where this point is.